All right, so we'll go ahead and try this again. I changed my shirt. I don't know. Maybe that's why. No idea. Now it seems like some people are having a hard time coming in. Okay. Okay, so apparently it's working now. Cool. All right, so let's repeat this. I have this wine glass here. It's filled with just a bit of water and it's set on top of this napkin. I'm just gonna wet my finger with just a little bit of water. I'm gonna place it here and I'm just gonna go around the wine glass in a circle. I want you to listen. Oh, put a little more. Put your volume all the way up. I wanna make sure you hear this. Of course, now it's not working very well. There we go. Okay, so you still hear a ring, ready? Let me do it again. I'm going to take my finger off and listen. It's still vibrating. So that's the reason why we have the thumbnail that we have up top. And that's because we're going to have an aim for this lesson, which is, why does the glass sing when I rub my finger on it like that? Why is it that this is all in, no, this is, yes, this is all backwards, isn't it? That's fun. Can I change that in settings? Is this backwards to you? Like, is it mirrored the wrong way? Oh, cool. Okay, perfect. For me, it is, whatever. So why is this thing singing? It's very strange, right? I take my finger and I just wet it a little bit and I rub it on the top and suddenly I get it to start making this sound. Well, we haven't talked in too much depth about sound yet, but there are just a few things we're going to need to establish before we go into this lesson too much. The first one, which you already know, is that sound is just a wave, right? It's a wave. It's an oscillation of the particles in the air. Now, for us, what we call sound is what you're hearing as I'm talking right now. If we're going to be technical about it, what you're hearing as I talk is the vibration of air molecules interacting with the inside of your ear. So if there's no vibration, you don't hear sound. You must have that vibration in order to hear the sound that's produced. So when I rub my finger around the glass, you hear a sound because that glass is vibrating air molecules, which were in turn vibrating what's inside your ear. Now, because this is live, you all can just type in any questions if you have them as I go along, and I'll stop and answer your questions. I'm hoping that's a nice part of this platform, instead of me just posting a video without any sort of interaction. Okay, so key to understanding this is this right here. I'm not going to put my finger on it. This time I'm just gonna tap it. Listen. Do you hear it ringing? And you notice every time I tap it, it rings a little differently. I mean, excuse me, the volume changes, but the pitch itself, the sound stays the same. Right? I can take another glass. This one has no water in it. I can flick it, different sound, right? But if I flick it again, same sound. So this empty glass makes the same sound each time, or the same wave each time. And this one makes the same wave each time. But those two sounds are different from each other. Okay. This thing, which is when I hit it, it produces the same sound each time, is what's referred to as the natural frequency. Okay, so this is the natural frequency of the wine glass. The natural frequency of each wine glass is different based on the amount of water that's in it. So there's a property of almost like, you know how the medium determines the speed? Here, what's going on inside the wine glass will determine what the frequency is when it's tapped. Okay, so I just have like a definition here. I'll put these on Classroom too, like pictures of them, so you don't have to write anything down. But this is the frequency that an object exhibits when sent into an independent oscillation. All right, independent, what does that mean? Well, it means that when I tap it, yes, I set it into an oscillation, right? Because I hit it, but now it's oscillating free of anything else. Nothing's making it oscillate but the glass on its own. Okay. A even better classic example of a natural frequency is a tuning fork. Okay, so here I have a tuning fork, and if I take this tuning fork and I hit it on this little rubber stopper here, can someone type in, can you hear it? Can you hear the tuning fork? Okay, good. Thank you. So hit this tuning fork and it creates a sound wave. This thing is vibrating back and forth very, very fast. You kind of see how it's blurry, and if I stop it, it becomes solid again. That's because this metal is going back and forth very, very fast at a certain frequency. Every time I strike this tuning fork, it will produce that same frequency. Or in other words, it will vibrate the air, making the sound at the same frequency each time. That's why you can use a tuning fork to do something like tune a piano string, right? Because if a piano is supposed to be playing, let's say, an E, I can take this tuning fork, which is labeled as an E, 320. That 320 means 320 hertz. That's the frequency of the tuning fork. And I can strike it and tune the two together. If I have another tuning fork, a different tuning fork, this one here, if we look at the two, we can see there are some different properties. This one is longer than this one. Because it's longer, just like the glass that has water in it, it will have a different natural frequency than this one, which plays the E at 320. This one plays a C at 256 hertz. So if I strike it, different sound. So this one versus this one. But if I strike this fork 100 times, I will always get the same frequency because that frequency is the natural frequency of the tuning fork. Yep, and exactly, Juliet. It's a lower frequency, so you expect a lower pitch. The final lesson that we're going to have this week in waves, it may be 2 lessons, probably 1, is going to be about sound and frequency, pitch, amplitude, volume, and how sound waves can interact with each other, just as a way of sort of bringing everything together. So I'm drawing some assumptions here before teaching the next lesson. So if anything is kind of tricky at this point, because we haven't learned the specific details, just send it in the text box and I'll address it now. Another thing that has a natural frequency, there are a whole bunch of them. A really good example is this right here. Now, this looks like it's just a binder clip attached to a piece of rope, but if I displace this binder clip and let it go, right, this thing now has a constant frequency or a constant period. It's a pendulum, right? This pendulum oscillates back and forth with some frequency. I can change that frequency. I can change that frequency by shortening my rope. If I reduce the length of the rope, I will have a pendulum with a much higher frequency, right? It's oscillating back and forth much faster here than if I make it longer and set it into an oscillation. This is also an example of a natural frequency because it's oscillating on its own. Yes, I displaced it. I set this initial condition that caused gravity to want to pull it down, but it will always, as long as I have the length of the rope this long, and the acceleration of gravity as g, it will always oscillate with this same frequency. Okay? I don't need something in here pushing it in order to make it keep doing that. It will just continue doing it. So here I have something. Pendulum has a natural frequency that's determined by its length and the acceleration due to gravity. And down here, I drew the two, right? I have this one, which is longer, and this one, which is shorter. And my two equations there, remember the period of a pendulum, I'm going to say frequency, we know it's just the inverse of the period, is 2 by pi radical L over G. So this TP, the period of the pendulum, could also be written as the natural period of the pendulum, or if we just conflate the two, the natural frequency. If I increase length, I will increase the natural period, altering the natural frequency. Okay, so a pendulum is a really good basic example of a object with a natural frequency. More complex one, a glass, right? When I flick it, a guitar string. If I take a guitar, right? Each of these strings has, again, I bought this at the perfect time. Each of these strings has a different frequency. And so if I pluck one, I get a certain sound. I want the guitar to be designed to produce the same sound every time. Otherwise, how can anybody possibly learn to play the instrument? It would be changing all the time. So when I design this thing so that it plays the same frequency every time I strike it. If the guitar is not in tune, I have something like this. Ready, listen. You hear how it changes? I've reduced the tension in the string, which therefore changed the natural frequency, just like putting water into the wine glass. I can tighten it, increase the tension. There you hear the frequency changing. That's the natural frequency, determined by the properties of the string itself, which you should remember from the last lesson has to do with the length as well as the tension. All right. So before we go any further, are there any questions at this point? All right, again, just throw them up in the chat if you do have them come to you. So in the table, I put other examples. I have the guitar string, a glass, a tuning fork is an example. I left some other dots here. I want you to think of what other things have a natural frequency. What other things, if you hit them, are gonna like ring or make a constant sound? Now, I want to continue talking about the pendulum, but I want to talk about a specific type of pendulum that you're all very, very familiar with. Juliet said, so I notice a pattern with smaller, shorter objects and higher frequencies. Yeah, that's often going to be the case. Very frequently going to be the case, because what's going to happen is you're going to have to increase the frequency. If it's a smaller object, it's going to require a smaller wavelength, and that smaller wavelength in an equal will result in a higher frequency, and higher frequency corresponds to higher pitch. And that's going to be part of what we're going to talk about a lot on the next lesson. Actually, Juliet will address that more directly, but there is definitely a connection between those two. The type of pendulum that I want to talk about that I know you're all familiar with is a swing, right? So you've all sat on a swing before. What is a swing? It's a mass here. This is the person sitting on the swing, and it's rotating about this axis here, and it's just a cord that's going down. If this person was to just kind of push the other person forward, they'd go up to some height and backwards. Why don't I draw that in with some color? I'll use blue. Okay. So if the person in blue pushes the person on the swing, the person would go up to this point here and then go back and forth. That person on that pendulum now has a natural frequency. They're moving at a period, which is 2 pi radical L over G, where that's the length of the pendulum. That's just the natural frequency. But now, what I want to throw at you is when you are younger, or maybe you still go on the swing every once in a while, when you are on the swing, it's pretty boring, right? To have somebody just push you once and go this high and go back and forth. So what happens? Your friend pushes you and you go up a little bit and then you come back. And then if you want to go higher, what does your friend do? Your friend pushes you, and you go higher. Let's draw this in. Right. So here, if your friend, you go up this high and then back, and then your friend pushes you, and now you go this high, right? And then you go back, and then your friend pushes you, and you go this high, and then your friend pushes you, and you go, this is getting hard, this high, right? And so your friend pushes you little pushes each time, right? Your friend keeps on pushing you just a little bit each time, and then each time it seems to get higher and higher and higher. Your friend would be unable to push you up this high in one push, right? Probably not strong enough. But if your friend gradually pushes once, push, 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 right? Your friend, the person on the swing is going to go higher and higher and higher each time. I can show this with my little thinky pendulum here, right? If I take this thing and I push it a little bit, it doesn't go very high. What I'm going to do is I'm going to consistently push it at the same natural frequency of the pendulum, which is determined only by the length and the acceleration due to gravity, and let's see what happens. Again, I'm not going to push it any harder one time or the other. I'm just going to limit myself to pushing this binder clip lightly. That's it, just like that. So make it a little longer. Watch. Okay, so you see, it started with those little tiny, I'm going to flip this, it'll help. Right. Oh no, it came out. Hold on. Oh, now it's like we're really in class. Where nothing works. And I'm constantly being censored by YouTube. Okay, so ready? Tiny push, tiny push, tiny push, tiny push. So there you see it. That amplitude of the oscillation gets bigger and bigger and bigger with each periodic small push, just like your friend on the swing. So here, what's key is that when your friend pushes you, if the swing has a natural frequency period this, your friend is pushing you at the same period. So we can say T swing equals this, that's F natural. If T push equals T swing, okay, the amplitude increases, right? So if the pushing force has the same period as the swinging force, the amplitude, which is this green line here, is going to get bigger and bigger and bigger. Now, that's really important because going back to my demonstration, again, in order to do this, I had to push it the same amount each time. I'm going to do it a little bit differently. If this is the natural frequency of the swing, I'm going to push it at a frequency that is different than that natural frequency. Ready? Okay, so right now my applied frequency is greater than the natural frequency. And so you see that it's not constantly getting higher and higher. It's kind of doing this erratic thing. And it's actually never getting as high as I was able to get it before. Oh, I'm not doing it right. Hold on. Right now with those small little pushes, it goes even higher. So that's when the applied frequency of me pushing is different. If it's less, you'll find the same thing happens every once in a while. It misses, sometimes it speeds it up, sometimes it fights it. It's not going to go as high. This isn't really working too well as a demonstration because it's too small of a pendulum, but hopefully that point is clear. This concept, which you're all familiar with, you've been doing this since you were in grade school, going on a swing, pushing your friend, making them go higher and higher. When you're like little, when you go to the swing, you don't just suddenly become stronger when you push your friend, but you're still able to lift your friend up much higher than you should be able to by pushing your friend periodically. or even when you swing, right? You like pull in and push out, and you do that, pull your legs in and then swing your legs out at the top of each point. You don't do it in the middle, you do it at the top, the 2 points. That's because as you do it, you are matching the natural frequency of the swing. This is called resonance. Okay? When you are being pushed on the swing at the same frequency as the natural frequency of the object, you are resonating. The applied frequency is resonating with the swing, excuse me. So this is the increase in amplitude of an oscillating object when an external frequency, that's the person pushing the swing, right, matches the natural frequency of the object, right? When we look at the glass here, I can set this thing into a natural oscillation at its natural frequency, and that's it. Eventually, it's going to fade down. It doesn't get any louder. It's only as loud as that first hit. Better yet, if I just take my finger and I do this, you probably can't hear. I hear a little tiny, tiny hum. Well, the loudness of that hum is actually the amount that the glass is oscillating back and forth. If I dip my finger in here, right, and I do this, now it's getting louder and louder and louder. Well, if that amplitude is increasing and I'm not hitting it harder, I must be resonating with the glass. And so what's really happening is on the boundary between my finger and the surface of the glass, there's a little bit of friction. And as my finger passes over that friction, my finger's kind of jumping a little bit. And it's jumping at exactly that natural frequency of the glass. And you can tell, listen to that pitch, right? Listen to that. And now that's actually the same frequency, right? Listen, and then, right? Very close. Okay, so that's what resonance is, and that's really pretty much all that this lesson is going to be about today. So that answers our aim, and we are good. Are there any questions? Hi, Bear. So Nelson, the reason why I need to dip my hand in the water is because I can't have too much friction. If I have too much friction, I just dried my finger off. If I have too much friction, it's not going to easily go over the surface, and so I don't end up with that jumping at the right frequency. Also, if I wet my finger a little bit, right? Now I have it. If I go too fast, oh no, it's working. Cool. Okay, it just reduces the friction enough. Are there any other questions? So we actually have another really cool demo that is at the school. I wasn't able to get it, and it's 2 tuning forks, right? So there are 2 tuning forks that have the same frequency, and they're stuck into wooden boxes that are open on one end, right? And so if I take these 2 tuning forks next to each other with the boxes facing one another, if I hit one of the tuning forks and then turn it off, the other one will actually continue to vibrate. So without actually touching it, I was able to get it to vibrate because the tuning forks are the same frequency. They resonated with each other, causing the other one to start shaking. So just, I want to go in order here. Michael asks, if you hit the glass anywhere, would it be the same sound? Yes. I mean, it'll be a different sound, but it'll be the same, like, I guess I could say like bass frequency. So ready, listen. Pretty much the same thing. Oh, also, you can see this pretty well, actually. I want you to, as I put my finger around, I want you to focus on the surface of the water. Watch it. You can see it vibrating, right? It's kind of hard to see. Okay. Michael says, does the water need to be in the glass in order for the glass to sing with a wet finger on it? Technically, no, actually. I've been able to get it without it before. Let's see. I have my other glass here. It's kind of hard, but yeah, probably not going to work. Yeah, it's pretty hard. Let me see. switch these glasses since I've had luck with this one. Now there's just a little bit of water in here. Hey, there we go. And you should notice that the frequency of the vibration has actually changed, right? Not quite the same. Nelson, also, there's like movie things where if you resonate with glass too fast, the glass will break. Yeah, Nelson, that is real. And in fact, it's a video that I wanted to post for you all. Hold on. Like the classic video of the opera singer singing and like the glass breaking is absolutely real. And here's a link to a good video by the Mythbusters where they explain the breaking of it. Michael, talk about those bridges and move. So Abir, that is what your homework assignment's going to be. So I'm going to hold off on doing it because you are going to be learning about it and addressing the physics in the homework assignment. And it's pretty remarkable. An entire bridge can actually be sent into an oscillation just from relatively low winds. Not low, but like 50 miles per hour. Oh, this is different Abir. Oh, hey, Abir. I was hoping someone else would show up because I made it public. So Abir, I don't want to go into detail about it because I don't want to ruin it for their homework assignment. Thank you for coming though. That's awesome. You're making up a 13th of my viewers right now. It's very sad. Cool. So if there are no other questions, I'm just going to go ahead and end the stream and post the homework, and you all can send any messages on Discord. The homework is going to be very different than any homework assignment I've given you before. You'll notice that like we haven't, I wrote the period of a pendulum equation, which you're all familiar with, but there's no reason for me to test you on that because you already know it. And so I decided to make your homework a little different. That's awesome, Abir. Makes me very happy. Cool. So last call, any questions? Do I know how to make Ethernet cables? I do not know how to make Ethernet cables. I mean, I'm sure could? No, Juliet, it's not, it's I don't know. It's not hard. I mean, I don't know. It's very different. He's making an Ethernet cable and he's confused. Is he just doing it for fun? Oh, that's cool. That's a nice quarantine activity. For games? Wait, why does he have to make an Ethernet cable for games? Tova, come here. Come here. It's really hot in here. Oh, so he's building it so that he can get it to his, so he can like hardwire his computer. That's funny. All right, come on, bud. Oh. Say hi. Yeah, that makes sense. Okay, all right, fine, dude. Go ahead, do you. Okay, I'm gonna go. Bye, everyone. Abir, thank you for coming. Everyone else, thank you for coming. I wish Edgar the best of luck with making his Ethernet cables. Cool. Bye, everyone. Don't forget to comment and subscribe.